Today I will speak about how to some guidelines, some hints about how to tune your neural network efficiently. So for you that are familiar with deep learning already, have heard a lot about this topic in the media and the conferences. Also, there are a lot of people investing on this topic and how try to make it more applicable in practice. So neural network, as you know, it's the main, it's what is behind the deep learning concept. So I will start with some basic notions about deep learning and machine learning, and then I will jump into more technical details because we have a lot of results to share, a lot of experiments to show how some parameters in the neural networks, how some parameters for deep learning, they affect the results and the performance of your analysis. So, and if you have questions during the presentation, something is not clear, please raise your hand and interrupt me. Last year we had a talk on this workshop about we showed basically the first prototype that we were developing. It was a beta version, and that time we were a little bit unsure about where we were going to get about deep learning and which kind of results we would like to get, and also what would be the capabilities of this technique. So, but this year we are much more mature on this topic. We learned a lot and from experiments, and then we basically we are trying to combine. We are combining and providing tools that we can efficiently apply deep learning in practice. So, but I can start saying some facts about the combination of deep learning and sidechain analysis. That I can tell you that we are still a little bit far from having one single button solution in this topic, because I think sidechain analysis requires a lot of expertise tools and background knowledge. So adding deep learning to that still adds a lot of requirements for knowledge and experiments. So we are, I think the research community, analysts, developers, everybody's working something that can become easier to use and more user-friendly, but it's still the experience of the user is still the mandatory part. So I would say that the current research outside that we have seen, also inside Riscure, what we have, we are still investigating the applicability of deep learning sidechain analysis. We already got some results that are quite impressive. We are seeing results outside that are quite impressive, but we still are trying to answer the question how a neural network recognizes features in leakage signals, and how this technique can be better than other attacks and to make the analysis more efficient. So let's start with what is the promise of deep learning for sidechain analysis. I can say that before we have the current situation, if you're using CPA, if you use template attacks or other more basic methods, we always need to pass through many steps, and this requires a lot of let's say background knowledge on every single step that you perform doing sidechain analysis. And going from acquisition, passing through leakage assessment, points of interest selection, where you identify where your device is leaking information, alignment, filtering, and also when you do supervised learning like template attacks, you need to train a model, you need to make it efficient, and you need to apply the model. So the promise for deep learning is that we're going to substitute a lot of man work that we have by machine work. So, and this is good from the applicability perspective, because we don't need anymore to suffer and spending time, that means money, on different steps that requires, let's say, a kind of boring work behind the scenes, because alignment, leakage assessment, everything can be done automatically. So some results already show that this is a reality already, and the replacement by all this manual work by the machine work is already in practice. So, but it's still the main question that when we do deep learning for such an analysis, it's like what we are trying to solve with deep learning, what do we want deep learning to do for us. So, and then this is the main question, not only for sidechain analysis, but a lot of different applications. So, and when we are saying that, okay, deep learning breaks everything, deep learning can classify everything very accurately, what exactly you mean by that? So who is doing this job for us? So this is what I'll try to show some results today that it maybe clarify this part for you. So let's define what is a deep learning problem. So let's say you have a lot of input data, and you want to classify this data. So you have a machine that basically implements a module that can receive this data and process this data and gives you what is the one class or the other, basically. So the machine must learn from the data and classify it. And let's say that if you take the machine after some training and then you provide one data, and the machine tells you that this data represents something else, not the class that you are aiming for. And the class that you would expect the machine to classify for you, it becomes, let's say, the second position. And then what you basically need to do is to use supervised learning to correct the machine and to make it more accurate. And this is done basically by observing what is the desired output that you would like to have, what is the actual output that you are getting, and then you compute the error. And then the error it's fed into the machine again, and the machine will update its internal parameters, its internal structure to learn from the data, and then doing this process many times it will learn how to classify the data more accurately, such that the accuracy of the model will go high and the error will decrease as a consequence. So what you want to achieve is this scenario where you provide the data and the machine tells you this is the real data that you are providing, and then you achieve some very high accuracy, you are done, you can apply the model, your model in the field. And this means that you are achieving good generalization, because the data that the data that you are providing out to the machine, it was not used by the machine to be trained with. So it's a new data. It never saw it before. So it's classifying correctly. It means, okay, my machine can generalize the different data. For sidechain analysis, we also have the same deep learning problem. But instead of some generic data, we have traces. And then in the traces, we need to classify them in separate groups. And instead of a generic machine, we have a neural network. As you can see, in the black dots, they represent the input layer. The blue dots, they represent the hidden layers. And then the orange ones represent the output layer. And let's say I'm attacking AS or I'm attacking this. It depends on the leakage model I select. And it gives me different number of classes in the traces. So my traces can be labeled with different classes. And then the output of my network will represent these classes. So for example, if I am attacking the S-box output of AS, I would have, using Hemingway model, I would have 9 different classes. And for this, I would have 5 classes if I'm attacking the same model. So, and also the same situation applies. I know what is my input trace, because this trace I know the key for this trace. And I expect some output, and then I also compute the error for this classification. Doing the computation of the error, I apply the error back into the neural network, and there is a very nice algorithm that empowered the application of neural networks in the field, that is the back-propagation algorithm. And so the back-propagation algorithm is the one that we're going to take the error, consider it, and then update all the internal parameters in order to increase the accuracy and reduce the error. So I will speak in more details about the back-propagation, because as we will show you, it's impossible to understand how a neural network learns and how it optimizes itself without understanding the backpropagation. So as the same example as before, so for sidechain analysis, let's say we have a target, we have one key that we know, and we train a machine, and the machine will obviously classify the system correctly, the traces from this target correctly, and will give us the key. But if we have a second device, this is the portability situation, where we might know or not the key, because we are doing validation or test, and we apply the traces from the second device into the model, and the model must give us the key as well. So if it generalizes to different keys, then we say that the model is generalizing. The models can break different targets with different keys. Obviously, as a situation for template attacks, the targets must be identical. So, but going now into more details about the deep learning itself, the neural networks, depending on the shape of your data, and also the algorithm you use to update the model, and also the leakage model you use, you can create a situation for defining many different hyperparameters. So let's say, as you can see here, this list is not, should not be limited to this one because there are more hyperparameters than this. And to understand the effect of all of them in deep learning is quite a huge amount of work. But there are some hints, there are some guidelines that they are related somehow to the way you are doing your attack. Let's say the number of traces you use, the number of samples in the traces, they will define how big should be your neural network. The back-propagation algorithm, it has all these features like learning rate, the batch size that you train, activation functions, loss functions to compute the error. So all of them should be tuned and defined for your classification, for your model to learn from traces. And also the number of classes that you have in the traces, depending on the leakage model, defines also the amount of neurons in the network. So if you have 256 classes, for instance, as you're using the ID model, you cannot use less than, let's say, 10 neurons to classify something because the combination should be high enough for the amount of classes you want. So up to 20 different parameters can be seen in this kind of thing. So what do we do? This is the time to panic because, okay, how much time do I need to learn in order to do this, to be able to tune all of these parameters? So there is no answer, a single answer for all of them, but there are many experiments you can do step by step and understand how you can tune one by one and how you can optimize one by one. So, and this I'm going to show. There are thousands of experiments that I will show here today in some charts, and then you see that some parameters really make sense when you're doing sidechain analysis. So, if sidechain analysis is already a difficult task to do in practice, deep learning is even more difficult because we have two difficult problems to solve. We need deep learning to extract keys from traces, and we want an efficient neural network for that. So it's a too difficult situation that you need to solve. So, but if you solve the second one, you also solve the first, of course. But there are many solutions to build a neural network, and let's say you can use artificial intelligence for that. So what I'm saying here, you are using artificial intelligence to solve artificial intelligence. So, but this increases even more the difficulties you're going to have. Or you can just define, okay, I have these parameters, fine for me, and then you just throw it on GPUs, TPUs, whatever, in the cloud, and then you wait for the computation and for something good to pop up from the result. So this can be done, but it requires a lot of investment. But I would say that before, the user experience is the strongest tool that you can have. And it's much more efficient than the first two ones. So I would say that when you start with, you have your traces, you have your target, your targets might be protected, might have some countermeasures, might have some misalignment, and you want to start attacking it with deep learning. And you have no idea where to start from, so I would say, or you start very simple or you start very complicated. Don't try to guess what are the good parameters for your situation. And you start very simple with a very simple model and you underfit it. The network doesn't learn anything. And then you jump to something more complicated and then the network overfits the data, but doesn't generalize. And then you know you are in between two extremes and just need to converge down to a good point. And to do that, you need to observe some metrics, like accuracy, the error of your model, the recall, that is a very interesting method for imbalanced classes like Hamming weight, Hamming distance. And as an example here, what this, I would, just to make a parallel, if you see the application of deep learning, let's say for image classification, what they want to have is 100% of accuracy or something close to that. Otherwise, it's not applicable. But for sidechain analysis, you don't need a model that classifies everything with 100% of accuracy. Let's say if you have 9 classes in your traces and you try to guess randomly what is the class of one trace, you have 1 by 9. Let's say this 0.11 will be the random guess. And that's the accuracy of a random guess that you get from the traces. And if you have a model that can classify the traces with something slightly above the random value, and you apply this classification results into a key enumeration, if you have sufficient amount of traces, this might succeed. So you don't need to go for 40, 30, or 90% of accuracy. Something slightly above the random guess is good enough. And this is an example of a trace set that is completely misaligned. And it required a lot of time to train, something like 30 minutes. And we got 0.12 as let's say, validation accuracy. And it was sufficient to break the target. So we don't need, even if the classification is, the accuracy is very poor, it's sufficient to recover the key. And so to observe the metrics like accuracy and recall is very important to define where we need to go when you are trying to tune your neural network. So first you need to forget about generalization, because what you need to have is a model that learns from data. And the learning curve can start quite late if you observe if you take some different scenarios. So be patient when you are doing the model training, because it can take several epochs, several iterations until it starts learning. So, but when you start observing what you are getting, let's say, it starts learning a little bit, but the accuracy is still very low. What do you do? So you need to start asking questions to yourself like, what do I need to modify? Do I increase the number of layers? Do I increase the number of neurons? Do I modify my learning rate? That's one parameter I will talk about. Do I need to wait more time? So if you do some modification and you start to see that your model now, the accuracy is really high, and then you also need to check, is my model overfitting the data? It means that we will not generalize. Or should I apply some regularization? That is something I will also speak today. And so, is my network too large? So there is some balance, and then you need to converge into something in between. But also, to get the answer for this question, you need to understand how the network learns something. What the network does, that it learns from data. And for sidechain analysis, there is a specific task that deep learning should do for you. So if you have traces that are collected from some specific target, and then you zoom in these traces and you overlap some of them, you can observe that there are some information that represents noise and some information representing data leakage, which is dependent on the intermediate value being processed. So what the neural network must do for you is to differentiate between these two kind of information, because in this case you are not providing points of interest. You're not telling that this is the region I want to attack. You just select everything. And the network must discard what is noise and what is not noise. Who does this kind of procedure is the back-propagation that I spoke before. So the back-propagation basically gets the error from your classification, and it updates the internal parameters of your network based on this error, and also based on different many hyperparameters that you define. So for instance, let's say that between two neurons here we have a connection, and this connection has a weight value. The backpropagation for every connection, it asks itself, how much do I affect, how much do I reduce the error if I modify this value into this direction? So it does some calculations to see how can the weight values can be modified in order to make the error smaller. So let's consider this neural network with two layers, very simple, and we populate all the connections, they have some specific weights. They are all represented here with W, but they are different values. If we provide an input data represented by these some features here, I1 to I4, and then we do the forward pass in the network, all the connections will be activated with some specific value. I mean, every neuron. The connections are used to compute the activation values, and until you get the output value of the network. And then let's consider now that neuron in the output. And if we zoom into this neuron, we will see that it is receiving 4 different connections from the previous layer. So my I value here would be the output of every neuron that is connected before. Every connection to this neuron has a weight value. And there is this sum, the weighted sum, plus a bias value that defines the value of the neuron. And this output value will pass through an activation function. The result of the activation function will be the activation of the neuron. So we have basically three equations for one single neuron. We have the equation of the error, which will take this output value and see how wrong it is or how correct it is. And we have the equation of the activation itself, which can be defined differently. You can define the activation function. Examples you might have heard about some of them, like sigmoid, ReLU, hyperbolic tangent. So there are different ones that you can use. And this is responsible for the nonlinearity in the neural network, this activation function. And also you have the sum, that is the equation of the sum for the neuron itself, that is written here in the orange square. Circle, sorry. So the backpropagation, if you remember a little bit of calculus from the college, you see that it does some derivation, which is the gradient calculation on the error equation based on one of the connections. So let's say we are trying to understand how much the connection W0 affects the error. So how much changing W0 will change the error. This is the equation. So all the three equations now are using in a chain rule in order to verify how the gradient is activated, how the weight is modified. So this new value that relates how the error is affected by the value of the connection is multiplied by a learning rate similar to the current value and gives the new weight value. So sounds very complicated, but it's very simple. Actually, this is just one operation that the network does for every connection. It uses the learning rate and updates the value. So hopefully, after doing this equation, the error will decrease for the next time. So why deep learning is very computation intensive? It's because here is just all these calculations for a single connection. But imagine now a neural network with millions of these connections, and the backpropagation must do this same calculation for all of them. It's a lot of array computation that you have. So the learning rate that is used to update the value of the new, it needs to be correctly defined to not make your model to learn incorrectly and never reduce the error. So here it's just an illustration of how you can define correct or very low or very high learning rate. If the learning rate is very low, of course, the error doesn't decrease. And if it's very big, the error decreases quite significantly, but after you have a lot of instabilities. And if you have a moderate learning rate, the error will decrease smoothly, and probably then the learning curve will start to happen. And so on the right, you have like an illustration of how the loss function, this we say sometimes, this is the landscape for one of the parameters. And what we want to do is to modify to find the parameters of the value of W0 that reach the minimum possible value of the weight, of the loss, sorry. And if you have a very high learning rate, the jumps into this landscape will be so big that the model will never stabilize. So it always jumps around and never finds the global minimum. But if the learning rate is too low, you want to achieve the minimum value, and then the learning rate starts to decrease. But when it finds the minimum value of one valley, it doesn't have strength enough to go up and then decrease and find the minimum loss function. So this climbing situation that you have for the learning rate toward the minimum value of the loss, it depends. It will depend a lot of the magnitude of them, and it should be good enough to find the minimum loss function, the minimum value for the loss. So I have an example here. This is a practical example showing how the learning rate is related to the stability of the model. So let's say that we have some learning rate that provides this accuracy increase and this loss decrease. And here you can see that there are a lot of instabilities at some time. It means that if you keep training the network, the error will go high and down, up and down all the time. So we have some solutions for that, but the most efficient one is to tune the learning rate such that it decreases during the learning. So it can start with the same value, and after we reach some point here, we decrease the learning rate to provide stability. So this is also a feature that you can tune. Inspector also have this feature there. It helps a lot in some cases because you start learning correctly, but suddenly the model goes wrong, and then the key is not recovered anymore, but it's just because you are keeping the learning rate too high. So this slide will show a lot of results, comparing, for instance, how the learning rate affects the results in terms, and how it is related to the batch size and the number of epochs, let's say, iterations you train. The batch size is basically, it's a very simple concept. You'd have, let's say, 100,000 traces to attack. You don't provide 100,000 traces at once for the update of the parameters. You provide small pieces of these 100,000 traces every time. Let's say 1,000 each time or 100 traces each time. So why do you do that? Because if you provide everything at once, all the time, the error will be the same, basically, in all the epochs, in all the iterations. So you provide groups of these traces every time, mini batches of it, and so the error is different for every mini batch. And then the network will try to identify, to balance the error for all of them, and then it can learn, otherwise it doesn't learn. So for different mini batch size, I did an experiment, and also for different iterations, and you can see that if you have more blue, the accuracy is low. If you have more red, the accuracy is good. So the same parameters, but only changing the learning rate, increasing it a little bit, I can get much higher accuracy. So the same training, the same configuration, everything is the same. The only difference is the learning rate. So you see here that starting from the same point, I can end in a very higher accuracy just by tuning a little bit the learning rate. So this is what happens if you put it wrong. It doesn't learn, it doesn't provide any good result. But if you increase a little bit, let's say by a factor of 30, then you already have a very higher accuracy. So the size of the network is also something, of course, that defines the performance of the model. And by size of the network, I mean here how many layers you have and how many neurons in every layer you have. And I did this chart. It contains 500 different experiments to show you how the size of the network is related to the number of traces you are attacking. So I did so I couldn't run too much experiments if I would have millions of traces. So I started from 1,000. I went up to 9,000 traces, and the number of parameters it means that the number of weight connections. So probably here the biggest network contains something like 20 layers of 100 neurons. So this is why you have 40,000 parameters there. And you can identify different regions here in this experiment. A region that I call generalization, a region that I call overfitting. So what the red region tells us is that if the network is too big for the amount of traces I have, it will only overfit. It will never actually generalize. So the training accuracy, it will be too high, and it doesn't mean that the network is good enough for different data. It just means that it's overfitting. However, if I have a good balance between the number of connections, the number of weights, the size of the network, and the number of traces. The training accuracy is not very high, but it's not very high not because it's not learning, it's just because it's not overfitting the data, meaning that it can generalize. So there is a clear relationship between size of the network and number of traces. And also for the validation, meaning that this is the trace set that the network was not trained with. So it's the opposite. So more traces I have for training, the better is the generalization. And of course, less traces I have, bigger the model, more the overfitting I have. Is it clear? Do you have questions? I can proceed. Yeah.
Is the result for the one Xbox 1 byte?
Yeah, so this is the target I use it is AS 128 bits, and the leakage model is Hamming weight of the S-box out. So every dot you see in the picture is one training for the same trace set. The results of one training. Was it your question?
My question is a target focusing on the 1 byte.
Yeah. Oh, sorry. Yes. So this is just for the first key byte, and so For this target, I would have similar result for the 16 kibytes of the ES. But this is just for the first kibyte, just to illustrate in one. It would be possible in one chart. Yeah, good question, because this is important to mention also. So regularization. Now it seems that we are jumping to something completely different, but this is actually a very common topic that people in the community machine learning realize that should be implemented if you are trying to generalize to different data. So the regularization, it's a mechanism to make your model to not learn only the features from the training data, but also to be able to generalize, to classify different data when it sees different data. So this represents how the regularization works in practice. So in the learning, the amount of learning you have, more regularization you have, less your model will learn. But there will be a moment where they will match the amount of generalization, the amount of overfitting. So when you have this convergence, it's good. The model can be good enough for your case. Of course, there are some situations, applications of deep learning that this cannot happen. This here should be 100%, otherwise it's not applicable, like classification of image or voice. But for sidechain analysis, you don't need to have 100%. So if you have this convergence of a balance between generalization and training accuracy, it's good enough. So there are many different ways to regularize your model, and the most efficient way, I assume, is to balance between number of traces and network size. So increase the number of traces is a very efficient one. However, there are specific methods for regularization, like data augmentation, which takes the same traces and modify them somehow to increase, without, you don't need to measure new traces, but you just increase the amount of traces you have by modifying them. And dropout is it's a technique that turning off some neurons, like say, faking the fact that the network will be smaller. And there are two methods here that they call L1 and L2 regularization. That's basically weight decay methods. They are more, let's say, easy to work with, and they are very efficient. So if you have corrected values for this parameter, they are numbers like the learning rate. You can make the network much more efficient in the sense that it will not overfit too much. So the reason for using regularization is to decrease the overfitting problem. And if you apply the regularization L1 or L2, what you are doing is to add a term into the error value. So the network will think that the error is much higher than it actually is. And if the network thinks that, what happened is that the update of the weight will be smaller. So the weight updates, the rate will not be so high, meaning that the network will take much more time to overfit, because it always thinks that the error is much higher than it actually is. So here, experiment I made comparing the both values of L1 and L2. And you can clearly see that if the values are too high, both of them, the network doesn't learn anything. The accuracy is quite low. When it's blue, it means low, and red, it means high. And also when it's both values are very small, the network learns too much because it has all the freedom to learn. So the good balance between these two values clearly can be seen here in this part, where you have appropriate values for both of them. So they are somehow related. It's not random, the combination of them. You can see that if you have something that is very small, probably it does the effect of L2, it will happen after some time. But if you increase a little bit the value of L1, you are inside of this region that basically much more chances for you to have a correct learning part. So to complicate even more, there are different. So the backpropagation algorithm I explained before uses the stochastic gradient descent, but there are much more different algorithms that you can use for the backpropagation phase. So how can I put this in simple words? So every year there are conferences in machine learning, and they are always proposing new methods. So the third one here, Adam, was proposed I think 2 years ago, and so it's already very popular in the community. So, but it doesn't mean that a new method is better, and as I will show here in this slide. So for the target I'm attacking, using different algorithms for the backpropagation provides you a different result. So this is there for a reason, and so also in the frameworks we use. So it means that this should be, you need to choose these parameters as because it's important as the other ones. So yeah, in my case here, using this, the backpropagation algorithm combined with this updater was better. So these two provide similar results, but the Adam, that is the newest one, or SGD, RMS propagation, they didn't provide me good results. So this is an important choice as well. There is a part here that would deserve an entire presentation, that how to configure the convolutional neural network. And I will slightly touch this part because it requires also a lot of discussion, all the other parameters. But I will just show you how tuning the parameters for convolutional neural network also affects that. So let's say we have some trace set, and then we implement some misalignment artificially in that, because we are the claim is that convolutional neural networks, they can recover the key even if the traces are misaligned, and it actually can. So if I have a very simple convolutional neural network, let's say with one convolution layer, one pooling layer, and in these two new layers here that were, before we were discussing about density layers, but now if we have these two new layers here, it also has a lot of parameters to define. So it makes our life even more complicated. So here is an experiment that I made, just for you to see that also for convolutional neural networks, the filters that you define in convolution layers, they also need to be balanced with some specific values and specific dimensions. So, but the good news is that, as you can see in this chart, there is some values that are more stronger for this application, but they are quite spread. So they are not really, the network is sensitive to these parameters, but not so much. So the relationship between the value of these parameters and the amount of misalignment is something that we are trying to find out. So how many samples are shifted here, and what is the size of the filter that you need to define? There is also a rule for that. So after we go, there will be some demos there. I can touch this part if you are interested. I can show live. So because this can take a lot of time to explain, and I think my time here is a bit limited. So, but then there is some good news that all this parameter search or all this definition of parameters can be automated. And for some targets, this can be quite trivial to do. But if the amount of leakage in the side channel leakage in the target is not so big, of course it will take much more time for an automated method to identify the neural network configuration for you. And so here I have an experiment of genetic algorithm. And in this case, I have a neural network where I don't define basically anything. It's a multiple layer perceptron, and I tell to my algorithm, okay, just search everything for me. I don't want to define anything. And these results here show that through many generations, in this case I ran 100, the model starts to increase the accuracy for the best individual. So automatically it will start with very poor accuracies here in the first generation, but after many trainings, it will be converted to something higher. So if you just define some ranges for these parameters and then you press a button, after some time there will be a configuration that is good enough for that target. And here is when you do the genetic algorithm in a situation that is a little bit more optimized. Let's say I assume I already know some of the parameters, and I want to search for some of them that are more sensitive. And you can see that now, just because I select some of them that are already correct, the accuracy for all the generations are really high. So before we were achieving something like 40%. Now we are achieving something like 60%. So just because we fixed 4 parameters. So some takeaways from the presentation, I would say that it's my conclusion that artificial intelligence, they can automate tasks, can make everything easier, but the user experience and the usability of the tool and then the experimenting with that, it will be the strongest. It will be what makes you understand better how this thing works and how you can convert to the correct application. Also, metrics that you get from the analysis is also, it's what drives you into this direction. So the understanding of the backpropagation is important. It's really not, let's say, crucial, but it's important for every step you make in terms of optimizing the analysis. So this is the state of the art for such an analysis, I would say. But it's just a starting point. So I think in a few years or months, there will be much more novelties and nice results and things that will make this application easier. Because now we know what we want to do. What is missing is just how to combine all of these things in less operational things. Let's say how to make it easier to apply. And I would say that I could realize from the research community that they are still investigating the usability of deep learning, but they are already convinced that this is a very promising tool for sidechain analysis and can be much better than the classic application. So automation will play a very important role in this part. Okay, so thank you for attending it, and if you have questions, I will be here all day. Yeah.